the Los Angeles area has acquired many secrets over the decades. Some of the most interesting took place just west of the city, in an area known as the Santa Susana Field Lab. There, they tested rockets and reactors destined for space. Because of this, they left behind a legacy of contamination that they have been trying to clean up. Today, I'm going to check out one of these locations, a basement that is radioactive from the years of reactor testing that they did down there.
So now what used to be here?
So this building here, you can see that white platform with the little doghouse door. That was building 4024, or the SNAP Environmental Test Facility. This entire site in Area 4, there were over 270 numbered structures. So in this area, there was some parking. There were a couple of other buildings around. So there was a power facility, cooling tower, but an entire industrial park to do the research and development for liquid metals and nuclear energy that was done here at the site.
Yep. Like, what are these guys right here?
So these, in fact, I'm going to phone a friend. So these are the old vaults.
Oh.
So you want to tell me a little bit more about those?
Yeah, so this is where they store the spent fuel. They're about 3 to 4 feet deep with thick concrete lids. And then they had a crane. You can see the system with the rails right here. And so they would take it from the building and then they'd bring it out here and they stored it.
Yeah, like very unique.
The building was constructed in 1960. The experiments were done all through the 60s. They decommissioned and decontaminated the building in the early 70s. I think some of the reports out there might have where the disposition of the fuel went from here, but I don't have that information offhand.
So now, are these still considered like an RCA area? Like if you were to take the lids off of them, or?
No, they actually did a survey in the early 2000s when they started the process of tearing the building down, and these were clean.
Were they originally like stored with like water in them for shielding, or?
Oh no, they didn't. There's probably water in there now, but no, that was not the intended purpose.
Okay.
The concrete is the shielding.
Oh, okay.
Yeah.
Yeah, I only asked that because of like coming from Santa Onofre, where they had like spent fuel.
Yeah.
And they had a fuel pool there that they would keep like all of the hot fuel that would come out of the reactor.
Right. But you're talking significantly more.
Yes.
Yeah, this is very, very small. When you go down in, you'll see how the reactors were inside these vaults. You'll see how small it was. So you're talking a very, very small compared to a functioning reactor that producing energy for a city.
No, the SNAP reactors were intended for space flight. So size was the limiting, size and weight. You try to make it as small and compact and lightweight as you can. So they did build cores for these reactors, but I think the fuel elements were on the order of an inch wide and a foot long, and they packed them into one compact core. So we'll get into some of those details as we show you the test cells down there. So watch your step here. There's a lot of old, foundation footings that will hop up on you. So we all have to put on hard hats and a little dial.
So is there anything we got to worry about, like falling on us down there?
Odds of it are very slim, but we will be down the basement, and it's like 28 feet to the top here. So there is a slight chance or a slight, there's a possibility, but it's very, very slim.
More likely than not, these are for when we're going down there. The way we built the doghouse in this area, there is a really low beam that you have to duck under. And especially coming up the stairs with a little brim on there, we'll call it out for you, but it is probably the biggest hazard there is that low beam going down the stairs.
So now why is this a RCA?
Because it's the activation materials from having the reactors in there. The neutrons would go into the concrete and the metal cladding on the sides, and they would create activation products. Europium and cobalt are the two main ones. I don't know if Lucas, if you want to go into any more.
Obviously there's more activation from that. However, because it's been sitting here for so long, a lot of those have decayed out. It's like sodium. Sodium is not as prevalent Europium-152, 154, and cobalt-60 are the common isotopes. Also, another one is nickel-63, which is a really low beta emitter that lasts for a long time, like a 100-year half-life. And that's what's left in the walls and the vault doors that we'll find out today.
Watch when you're going down these stairs, and then you can see where the signs are to watch your head. So,
Okay.
here we go.
Quite a door.
So this is our 6-foot door, and then you've got over here, you want to see a bigger one, you've got a 9-foot door. Obviously it's going to be quite heavy, so put it on rails to go and seal these chambers.
Jeez. That is quite a plug. This is very impressive, actually. So now, what would it have been like the two different areas? Like, why would they have a bigger plug or bigger door, more shielded door?
They had 2 test cells. So this is the western test cell, and we can walk up over here. You can see there's water. So over the years, there ended up being cracks that groundwater will seep into the building. We pump it out, we test it. It doesn't have any hazardous components, so we just dispose of that water. So we get it pumped and just ship it off site. So, but this is the western cell. We'll be able to walk back from the other side. It's dry enough on the other side, great. And you'll be able to see there's vacuum pumps. So you would be able to pull this door in. This would be the shielding necessary. The reactor would go in here, and then they would draw it down to a vacuum with the big vacuum pumps and be able to test it in the vacuum so that's the intended use. It's a space reactor is going to operate in a vacuum. So we wanted to be able to operate in that environment, and that's what this building did. It's a big vacuum chamber. They've got this is the western cell, and I'll show you on the other side is the eastern cell. So we had 2 of those cells. So that's why this door is thicker here, is to provide that additional shielding. And then the literature doesn't have much about that I was able to see about what the central cell was, what it was used for. But so there's 3 separate chambers. It talks about so the western cell was where they tested the SNAP-10 reactor concurrently with when the SNAP-10A, the snapshot, was in space. It's the only nuclear fission reactor that the US has sent into space.
Because all the other ones have been RTGs.
RTGs, yeah. So the SNAP program actually had both RTG, and so that's the radioisotope thermal generator. So you put something that will decay, typically plutonium, a small pellet of that, and as it decays, it creates heat. And then you would use that heat to generate power. Those were the odd-numbered snaps. The even-number snaps were fission reactors. So this is where you create a core and then you let it go critical, and that's what generates the heat. They had a variety of different options. So the SNAP-10A, that's the snapshot, the satellite that was sent into space, that had a NAC, so sodium potassium coolant, that would then go to the thermoelectric generator. And so I've actually got a picture of it over here, so let me show it to you.
Okay.
We should do it side by side, because this picture, and I don't know if you can pan up, you can see that vault would be able to open up, and that's where they would lower the the snap reactor into here. And so the shape is obviously to fit in a rocket's nose cone. The reactor core is up here, and there's the metal beryllium drums that they would rotate to control and have it go critical. And then the NAC would take the heat from the reactor, and then all of these are thermoelectric generators that would take that heat and then shield it, radiate that off into space and generate power.
Wow. Yeah, so this is all aluminum, right?
This is aluminum. There's steel in here, but the cladding is aluminum. Is that correct? Yeah.
Yeah, that's what I was remember reading from the literature also.
I think it's steel structure, but the siding is aluminum.
Yeah. Yeah, which I think was actually to pull the vacuum.
Yes.
Yeah. So now what were these guys here? Were these like some sort of like access?
My understanding is these would be access ports for instrumentation that you would be able to run wires into it. That's the best that I can tell.
Okay. Probably also like just run the controls of the reactor probably too, I'd imagine.
Correct.
Yep.
Yeah. And there's all kinds of control rooms that, for structural stability, that mid-level, the first basement level, would have control room access on it. There may have been other controls down here. I'm not aware of exactly what it was before the decommissioning and decontamination that happened decades ago.
It's like, did they used to have like leaded glass here? So this is leaded glass and then filled with mineral oil and all that stuff? So it almost acted like a hot cell here, so then they could still...
Perfuming.
Yeah, okay.
Yeah, it's a wild concept, really.
Yeah, I know. Be able to see like into a spot that would normally
crazy.
kill a person.
a little unnerving.
Yeah. But this didn't have any test reactors in it. It was just the side buildings, right?
Correct.
So then what was in here?
I don't know.
Huh.
Maybe they're going to do another reaction, but they did not use this trans cell. They call it trans cell. They didn't put a reactor in here.
Also, another thing that's interesting, if you look at this, I guess you'd call it a screw. They would run that screw and shut this door.
Yeah.
Oh, wow.
And then we got another one on this side. And they would seal this chamber off.
So these are the vacuum pumps here.
Whoa.
So they would draw, my understanding is they would draw the entire chamber down into a vacuum, all three of these. And then when they had this all under a vacuum, they would be able to isolate the individual chambers and close these off.
I mean, to pull down, I guess, the vacuum in like this type of an area, it'd be a tremendous amount of force.
I think a lot of pumps and a lot of time, and they just, try and pull as many of the atoms of the air out of here as they can.
Very cool. So we can walk in this side of here?
So this is just that western cell.
Oh yeah. Yeah, we're just on the other side of it.
Yeah.
It's quite a plug.
It's worth noting the markings on the wall. So this is all in preparation for our demolition. We've done characterization many times over the years to understand the radiological impact of that activation. I don't know if we've mentioned what activation is. Activation is a form of contamination here. And so as you have a fission reactor, the core has the enriched uranium, and as that splits apart or has these fission events, neutrons will fly off. That's what will create the chain reaction. So we'll have reflectors that will help the core go critical, but some of those neutrons will just fly off, and that's really why you don't want to be next to a reactor, why we need all this shielding. But as those neutrons interact with the aluminum, with the concrete, with the steel, they'll get captured by those atoms and turn them into different atoms, some of which Lucas had mentioned before, europium, cobalt, nickel, now have decays of their own, and now we will treat that as our contamination. So that's why we've marked up all these walls in the grid and have the cores that you can see. Not all of the holes, some of the holes, the ports were originally there, but we would come in and we would take cores out and we'd be able to sample those and understand what's here after having the reactor run for 10,000 hours, over a year in this cell. So I think it was over 20,000 hours of reactors were operated within both of this western cell and over behind you on the eastern cell. Created all of this activation, and now when we dispose of this, we need to be aware of that and dispose of it in the appropriate license and licensed facility.
So now this is the other.
So this would be over to the eastern cell. So yeah.
Okay.
We can certainly walk over here.
Check it out. So now this was a smaller reactor?
So this one, and I'll pull out, we have our historical site assessment, and that, I'll provide that for you.
I just got a trigger on my alarm. Blocked by something.
Huh?
Went over half a microsievert.
Oh yeah, it's higher in here than in that trans cell.
Oh really?
Okay, yeah, so this is the eastern cell, and so the prototype SNAP 2 demonstration reactor operated for 5,000 hours here. There was a critical assembly 4B, SNAP 4B, that operated for a short time at a low power in the eastern cell. And let's see, and then also the SNAP transient test reactor also went critical, operated for a short period of time. Yeah, so not only do you have this is also publicly available on our website. So anybody who's interested in the historical site assessment for the Building 4024 SNAP Environmental Test Facility, SETF, we've called this a number of things throughout the years, but all that information is on our website.
So now how long do you think the deconstruction of the site's going to take, the demolition?
Right. The demolition itself, we anticipate on our schedule, it's about a year. We're anticipating, right now the schedule says that we would like to get that started in 2027. We've submitted the work plan to DTSC. They're reviewing it right now. We're going to work to hit that date to get this going by starting 2027, wrap it up in 2028. How far underground are we?
We are out in that main room. We're 28 feet down, and these cells are about 19 feet from the floor up to the top. So there's about 10 feet of concrete above us in these cells.
Okay. Yeah, I'm definitely picking up more activity in here. I could hear my detectors going off. So now these core holes are where they did like sampling.
Yep. So we would come in, we would pull that core, the cylinder of concrete out, and we'd be able to test that. So did it on the floor, a couple of locations. You can look behind you. You can even see the dates of some of these that were taken. So we've got March 1981, we've got a 78.
Yeah, that's pretty cool. Because it's like a little history, like what was happening here at that time, and then it's like such a controlled environment too that I would imagine like a lot of what was ever written on here stays on here.
Yep.
Yeah, as long as it's like somewhat permanent.
Yep, and it's not like we stopped in the 70s. We've got one from 2003 over here. So we've been, as much as we've been working trying to get the buildings demolished, get them disposed of properly. We've been sampling along the way to make sure we do it by the books, and again, with that mantra of safety first. We know that there's activation products in here. We know that they have decays and half-lives. It's a radiological controlled area. All of those things support our safe demolition of this.
So that's a dosimeter? That's a TLD?
It's actually a OSLD.
Oh, that's right. Okay.
Yeah.
So now what's the difference between a TLD and an OSLD?
So the TLD is a thermoluminescent, which means they use heat. Basically, they bring out the energy when they bring it back to the lab. And then these are optically stimulated. These can actually be used again.
Oh, wow.
Thermoluminescent is one time use, done. They're cheaper, but
Sorry, thermoluminescent ones, so it's kind of like film badges in a way?
yeah, pretty much, yeah. And then it just brings out the energy from, and then of course they can identify those energies. And then same with this, it's same concept, but it's optically stimulated instead of thermo.
Pretty cool. Yeah, you guys just leave it down here and then just check it every quarter, or?
Correct. So we replace them every quarter. So we have multiple years of how much is in here 24/7. So we don't remove these, we leave them here. And then we get those reports back and we go over them every quarter and review it. So if there's any abnormality, we make note of it.
And we share all of that information. So going back to the 1950s, we have annual site environmental reports. We call them ASERs, ASER. But all of the data that we collect here, all the data that we collect across the lab. When you were here last time, we showed you the air monitoring station. All of that data, we do groundwater monitoring. So it's across all of DOE's portion of the Santa Susana Field Lab. We grab all of that data, we put it in a report. They come out every year.
Like, where was the reactor situated in here?
It would be in the middle. So that's
like
the
right.
plug.
Oh, it's like right. So I'm saying like right where it would have been. Okay.
Yeah, that's your plug. That's where they drop it in, right? That's where they drop it in and they pull it out. It's right there. And the building there used to be a crane. And I know you can't see it because it's not here. Yeah, it's unfortunate. But the crane, obviously it had it. It wasn't that big of a crane either. And then they would use that to pull the plugs. And it's 3 layers of it. So it's not just one big giant piece of concrete. It's multiple pieces that they would pull up.
So it's like concrete, steel, concrete. Yeah.
Very, very thick concrete.
Yeah, just to provide enough shielding because they had like offices and stuff above the reactors.
Not directly above. Some of them, the control rooms are like right up here in that corner.
Oh, okay.
And then they had another one outside in the rubble. And used to be there.
That'll be interesting when you guys start taking that apart. It's like to get all of that material out of there. It's like.
Yep. No, there's a lot of concrete. You saw those doors. I mean, that's the part that we can move in and out. But I mean, you can see.
Yeah, I know. Well, it's interesting, like how it's also ribbed, like to create like a path where the radiation can't get out.
Right.
But also it's also to try for the seal in here, too, to provide that vacuum.
Yeah, I wonder. In fact, I haven't looked. I bet there's probably they would have had to.
You think it was like a gasket on this?
I know.
It feels like there might have been.
They would have either done a gasket or maybe some sort of.
I mean, it does feel like there's like a material on there.
Material, something that they would create that seal, because you're going to draw that down for a vacuum. And I mentioned these are 5,000 hours, 10,000 hour tests. You're not going in and out. You turn it on, and this needs to keep a vacuum for a year plus.
I can walk around and I can like hear it. Like with one of my meters here. It's like giving me a super high count rate, but it's definitely more active. And if I switch it over to dose, so yeah, I'm only getting like 0.25.
Yep.
Yeah.
So I'm in micro R, and I'm around 30.
Okay, that makes sense.
Yep.
Yeah, that's right around the same. Yeah.
And
same
this is the Geiger, so it overreacts anyways.
Yeah, there's definitely like, it's low. But it's definitely around here. And I'd be curious to see, like, this is also pulling like a gamma spectrum too.
Yeah.
So this will actually be able to show like what it is that we're looking at.
Yeah, you absolutely will detect it.
It's like, it just feels like it's like all the way around here.
I'll show you. You'll see throughout here you have the dates and then you have a number. That's actually the counts per minute that they have.
Oh, wow.
And they wrote it directly on the wall. So when you when you're looking around, you can see they found hotspots. And I put that in quotes, hotspots, because 59,000 counts per minute really isn't that substantial. However, it is the readings that they got. And then if you look around, you can find it from different years. And they'll give you different numbers. So
do you know like the type of detector they were using to?
Yeah, so that's with the sodium iodide probe. So very, very sensitive. Yeah, so put it up to there and see how many counts you get. I'm sorry.
Yeah, that's all right. Yeah, I mean, I'm only getting, let's see here. I'm getting like 1,500.
Yeah.
1,500 counts? Yeah, which is significantly lower than 64,000.
And remember,
and they also probably were using a 2-inch.
There you go. Yeah, that's exactly.
Yeah, because since this one only has like it's like a 1 centimeter cubed detector, it's a lot different when you're using a much more sensitive detector, like a 2-inch, sodium iodide detector.
And we call it a 2x2.
Yeah.
Because of the crystal. Yep.
Yeah, it's gonna be way more sensitive. Like it's like I am showing radiation here, but nothing even close to the numbers that you guys got when you guys were doing your survey. Yeah. So that was back in 2018.
Mm-hmm. And there's some other ones you can find from 2003, 2006 range. And then obviously all these other ones are core samples. Now again, the core samples are really helpful. And it's kind of fascinating because what you can do is you can go back and you can look at where it actually penetrated and how far it penetrated based upon your core sample. And then you can also get for the reason for the core samples is because that's what you're trying to find out what's the concentration of each isotope for waste disposal. Those facilities have to know very strict requirements. What do you have in this material? You need to tell me exactly what's in this material. And that's why we have so many core samples done throughout the years, is to say, this is how much we have. And then they also know this is how far it went into the concrete.
And that goes to a facility's waste acceptance criteria. So this isn't going to go to your local landfill. This is going to a licensed facility. We're still getting the demolition plans approved, so I can't tell you a specific place where this would go. The discussions we've had, more likely than not, it'll go out of the state of California to a licensed facility. These waste facilities are engineered. It's not just the geology, that needs to be right, but then they engineer to make sure these last as long as they need to for the waste that's coming in. And that's what helps them define the waste acceptance criteria, because just like us, those waste facilities are safety first.
This is all aluminum, right, on the walls?
Aluminum, and then you can see here, it's, oh gosh, I don't know the thickness I could estimate, but then it gets to concrete.
Yeah. Oh, that's all right.
A light for you.
Yeah, it doesn't look like a ton of material on the side here. Yeah, it looks like it just goes like a little bit of metal and then into concrete.
Just trying not to step on it.
I know, it's so loud.
So some of it, you can just put your meter up here and you just try to find a spot. And sometimes you get higher readings than others. Here's someone that wrote on here 57 micro-R, and I have it on 250, and I'm at 50, roughly 50 micro-R, if you can see that.
Okay. Yeah, I'm curious.
You know, it'd be more fun to walk up to it and show. Because
it's still very low. Like,
right.
Yeah, it's like a little higher here, like 2,000 counts per minute. Yeah, but I would imagine that the dose is still pretty low. Yeah, it's almost half a microsievert.
Yep.
Yeah, which would check out as far as what you're seeing in micro-R too.
Exactly.
Yeah. Still very low stuff.
Right.
Yeah, but yes, it is radioactive.
Absolutely.
Yeah, that's like. Huh?
There you go. There's a good spot.
Yeah, there's something there. Oh yeah, a little bit higher.
You got the alarm.
Yeah, well, it's set pretty low. Now it's up to like 3,000, 3.5. Yeah, I wonder what. So that makes me wonder, like, what was right here where they would be getting like a blast of neutrons? Like,
well, you know, what's going to happen is those things go everywhere.
Yeah.
And neutrons are neutral, so it's really hard to absorb them.
Exactly.
That's the reason why you have all the walls, the thickness, and it's a neat concept in the sense that it wasn't in here, so how did it get over here? And a lot of that's just bounce. I mean, it just bounces around, and it doesn't interact with the.
Well, also there's fast and there's thermal neutrons.
And thermal,
too.
it's more thermal for these test reactors. The energy levels are lower.
But thermal is usually what gets absorbed by material easiest.
Oh, 100% it does. That's the activator. That's what creates these unstable atoms that we were talking about. And thermal is very, very common in reactors.
A little bit hotter there. I mean, nothing like crazy, but yeah, it was like interesting to see that. I'm curious to see what it is with my Radeye. Yeah, pretty low, even just down here.
Is that helpful?
It's a little too big. Thank you though. Yeah, appreciate it. Yeah, no, this is like barely anything. Yeah, it's like 120. It's a little spot right around here. So this is good because it's like good to find an area. Yeah, it definitely seems like right around here. Maybe like this is where they gridded it out. It's weird that it'd be like over here. Yeah, definitely like really isolated. Oh, it holds a little. So you think this is primarily, you think it's cobalt or europium?
Well, it's going to be both.
Okay.
So first of all, one thing is that this aluminum is going to shield that concrete, right? So you're not going to be able to see it as well with that, whereas with these guys, they're going to be able to still see it.
Exactly.
But you're picking up both because you still have high enough energy from that europium that you'll still be able to see it, and then you're seeing the cobalt 60 as well.
Yeah, but it's incredibly low. Like with this meter, and that's this is something I use all the time for, surveying like uranium mines and stuff like that. And yeah, it's very, very low. Not like the scintillation detectors. Like what you said, it's like mainly just gamma radiation.
Yeah.
Because the betas and everything else is going to be, or betas, so it's just going to be blocked by it.
Well, in cobalt 60, you should see that because of the beta. Yeah. Right? But that europium, you typically won't. You're going to just get the gamma from there. And then they also are alpha, which we're not going to see any of that at all. And then
it doesn't go very far.
Correct. Well, you got your own shielding.
Exactly.
Yeah. And just a reminder that this is all fixed. So we come in here and we do routine surveys, and we bring down swipes that we analyze on our instrumentation that I showed you when you were here last time. So we pick new areas every single time we come down here because we want to just do as much as we possibly can. And we just grab swipes and run them, and we just nothing's removable because it's all in the wall, fixed. So once we start demo though, that's when you can start to break that up.
Yeah. I mean, I guess the good thing is that it's already in a pit underground, and so to be able to control that contamination is a lot easier than if it was out in the open air.
Agreed. Yeah, a lot easier to do that, absolutely.
Talking about demo, one of the things that we did with our 2020 demo, we'll certainly do it again. Not only do we have perimeter air monitoring, but we will have localized air monitoring. So we've typically put 3 air monitors, 1 upwind, 2 downwind, around the local area of the site. We'll do that again this time. Other controls we'll put in place. We'll make sure we have a cultural monitor. This is a sacred site to the Native Americans. And so while this was disturbed more recently, 1960s this was built, we're not expecting to find anything. We still have, it's a National Historic Preservation Act, Section 106 programmatic agreement with the Native Americans that says that anytime we do anything that's going to move the ground, which we certainly will here, we'll make sure to have a cultural monitor, so somebody from a local tribe will come and monitor everything we do in case we find anything that could be of significance, so we can make sure we document that and understand how to not disturb that or disturb it appropriately as we proceed.
Yeah, it's like I'm not even getting like anything really. Like I get something right here, like a little bit. Yeah. Getting, it's like, like 114 caps per minute. I mean, really, really low with this detector because it's just not as sensitive to the gamma radiation. Yeah, but there's definitely, I could see like there's definitely like parts that like. Yeah, very, very low. Yeah, I could definitely see where the slip, trip, and fall thing is a big deal here. Like these big gaps. Like, so I'm like walking around here, like where am I? Like,
always watch your step.
yeah, I know, especially around here. It's like. So now, what happened to the plug that was in here?
We don't know. The documentation of where that went is not something I've seen yet.
I know, it's like how did you guys? It's like getting like a ship out of a bottle, because the thing would have been huge to fit into this cavity back here. So it's like, where did it go? That's why I noticed. Like when I first walked in here, I was like, there's no shielding plug here. Yeah, must have been a magic trick.
a good magic trick.
Yep. I didn't see a lot of readings on that one either. Is there like a lot of surveys?
Oh, you know, there's definitely readings.
Oh, okay.
Yeah.
I was just noticed it since you like said that. I was like,
And you know, you would get, I get some of the higher readings on that back wall, just like on that other
Oh, okay.
spot. So some of the higher ones right here, you can see these guys, they found one that took
Oh, yeah.
a floor at 98,000 back in 2012.
okay.
And then you can see one over there, 78,000, they just wrote on there in 2018. So there are definitely some, and and then we also have a dosimeter in here as well.
It's too bad like you guys can't like keep this, like, cause like you think about like EVR1 and stuff like that, and like how like that's like a touristy place.
Yeah.
Like that would be pretty cool.
I agree, and so I mentioned the National Historic Preservation Act for the cultural side. There's also the recent history side. I think it's if a building is over 50 years old, something along those lines, it could be considered historic.
For that.
Right.
Almost. Well, actually it is, yeah.
But you'll notice that we were decommissioning this in 1978. So we stopped doing the testing in the late 60s, early 70s. I haven't looked at that. But within a decade, we said, okay, we're done with this. This is excess. We're planning to demolish it. This inspires our work today, even at the DOE, not just with the scientific progress that was made in facilities such as this one, but the innovation across what we're doing.
I think it's like really cool for a lot of people to see this stuff, because I think it actually maybe inspires a lot of people to learn more about the subject.
Absolutely.
And that's why I like doing these videos, because I get so many like comments and like things like people like wanting to learn more about this subject.
Yeah.
And so I think that maybe there's even like, you know, kids are probably seeing these videos and like they want to like, well, maybe that's what I want to go into.
Sure.
You know, like that
that's
type
what
of field.
that happened for my dad. I mean, this is in the era of the space race. My dad worked at NASA, and you know, he was an engineer there. He inspired me, but he was inspired by Sputnik. I mean, that's what inspired this as well. The problem was, hey, we want to do more, longer, further into space missions. How do you power them? Solar power in the early 60s was not going to power your satellite, power your mission. So what's available? Well, let's look into nuclear. Does that work? They had a couple of different concepts. We mentioned the RTG before, but can we launch a small fission reactor into space and have it work? And we did. We successfully launched it into space. It ran. It's still orbiting today. It's planned or it's in a polar orbit, 800 miles into space, and it's going to orbit for thousands of years.
Careful going up these stairs, and then when we get further up, I'll point out that beam that we got to duck under.
At least you guys got a bunch of foam padding on it. Where are the plugs for the access to go straight down? Is it underneath underneath this covering?
Oh yeah.
Oh, okay.
They're in here. So you would see the rails here. Those rails line up.
Yeah.
So they would have been, I don't know exactly where, but somewhere.
Yep, right about here.
Yep.
So you
Okay.
had 1, 2, 3. And all the plugs are right here. The layers of plugs.
This would be above that west reactor. Oh, sorry, that would be the west reactor. This would be the east reactor chamber.
All right, well, that's going to do it for the Santa Susana Field Lab, or Rocketdyne tour of building 4024, more of a basement, really. That was the Snap reactor test site. And it was really cool to go down there and actually check out this site, because I don't really get to see a lot of former reactor sites. I mean, there's like EBR1 and maybe going to Santa Onofre to see some of those places, but nothing that was actually built specifically for the space program. So that was really interesting to see. But anyway, hopefully you enjoyed this video, and I'll see you in the next one. Take it easy.